Hello, I'm Shahbaz Abid. This is General Physics 1 Lecture 2. From this lecture onwards, I'm going to discuss about motion in one dimension. Any physical quantity can be described as a scalar quantity or a vector quantity. Now, a scalar quantity is those physical quantities which actually uh, just need a magnitude, no direction. Whereas the vector quantities are those quantities which needs both the magnitude as well as the direction. The examples of the scalar quantity are mass, temperature, speed and distance. Now the speed and the distance I have written in bold letters. These are the two which I'm going to actually describe in this chapter. In the case of the vector quantity, the examples are velocity, force, acceleration and displacement. Again, I'm going to describe velocity, acceleration, displacement in this lecture video. The scalar quantities can be added together, but the vector quantities actually requires vector operations, which we are going to discuss in the vectors chapter. As I mentioned, in the vector quantity we need the magnitude as well as the direction. So for the direction I must specify the coordinate system. Now what is a coordinate system? It's actually going to tell us the position of an object with respect to that coordinate system. Now there are two types of coordinate systems very popular. One is Cartesian coordinate system and one is polar coordinate system. Now in the case of the Cartesian coordinate system, we have a positive x-axis towards the right and the negative x towards the left, and the positive y to upward and the negative y downward. Since we are going to discuss motion in one dimension, it's going to have a motion along x axis only or along y axis only. That's why it is known as one dimension. Now I have mentioned the quadrant also as well. In this case, quadrant 1 is going to have plus x and plus y, quadrant 2 is going to have negative x and positive y, quadrant 3 is going to be negative x and negative y, and quadrant 4 is going to be positive x and negative y. This we need to remember in the vectors chapter, so this is just an introduction for that chapter as well. The origin is the intersection between the two dimensions is going to be 0 0 0 x and 0 y. I have given an example of a two dimension object location or position. In this case is going to have x equals to 2, it has traveled 2 units, and y equals to 3, it has traveled 3 units in the y direction. So the location is 2 comma 3. I have another type of coordinate system which is known as polar coordinate system. Now in the case of the polar coordinate system, the object position is specified based on the distance from the origin to that object and the angle created from the x axis. That is going to actually specify us the exact position of that object. Now there is a way to convert Cartesian to polar and polar to Cartesian, but we are going to discuss this thing again in the vectors chapter. The position symbol is actually denoted as x. Distance and the displacement are the very important topics in case of the motion in one dimension. The distance is basically a total path traveled by an object, regardless of its direction. So it means what? It's a scalar quantity, it does not depend on the direction, so it's always positive. We can just add all the distances regardless of their direction. The symbol of the distance is d. Whereas the displacement is actually a vector quantity, and it is actually a change in position of an object. So position means it's a vector quantity, so it's actually a change in position. Change means you need to actually have final position and the initial position only to actually get the displacement of an object. Now the displacement and the distance are not equal to each other most of the time, but the displacement can be less than or equal to the distance. And the important definition of the displacement is actually the displacement is the shortest straight line distance between the 2 points. So the displacement can be less than or equal to the distance, but it cannot be more than distance. So let us prove or justify this statement. Let us have a path A B C D A. So I have this picture. Let's say I went on a hiking, okay, and my position is at A. So let's say if I have traveled from A to B 250 meters, from B to C 250 meters, from C to D 250 meters, and from D to A again 250 meters. The total distance I have covered is going to be 250 times 4, because it's going to be 250 plus 250 plus 250 plus 250. So distance is always added together. So it's going to be 1000 meters. But what about the displacement? I have traveled this whole path just to come back where I started. So it's going to have final same position and initial same position. So it's going to have displacement equal to 0. Okay, both of them are at the same location, so it's going to have a displacement equal to 0. So this actually justifies that displacement is less than distance. Now let's choose path AB. So for example, if I have traveled from path from A to B, the distance I have covered is 250 meters, and final position, if I'm going to have an origin at A, I have covered 250 as a final position, and the initial position was having a 0 value as a position. So I'm going to have a displacement equal to 250. Now you can see that they both of them are equal to each other. Let's choose path ABC. So I have traveled from path A to B and then B to C. Now the distance is going to be A to B 250 and B to C again 250 are added together. So it's going to be 250 times 2 is 500 meters. Now the displacement is the shortest straight line distance between the 2 points. So in this case, the shortest distance is going to be from A directly to C. So it's going to have an arrow starting, the displacement arrow starting from A and ending at C. So this is the shortest distance that you can travel to reach from A to C. So in this case, how we can calculate it? It might look like a 2-dimension motion, like you are going from horizontal to vertical, but this is just to say that this is the shortest distance between the 2 points, and we can actually get the displacement by Pythagoras, and we are going to get it as 353.55 meters. But this is going to be discussed in the vectors chapter, but I wanted to make sure that we understand what is basically a displacement. Displacement is always the shortest straight line distance between the 2 points. There is no other distance less than this displacement distance, which is 353.55. So if I'm going to choose, let's say, a path like this, it's not going to be less than 353.55. So the shortest distance between A to C is actually 353.55, and the displacement direction is always from starting from its initial position to its final position. So the arrow is going to move from initial to final. We are going to use the distance and the displacement in speed and velocity. Now in the case of the speed is a scalar quantity, and it's actually going to tell us how fast an object is moving. Mathematically, this means what? The speed is equal to total distance divided by the total time. The SI unit of it is actually meter per second, because we are actually dividing the length by time. So it's going to be meter per second speed. Let's see an example for the speed. A car travels 180 km in 2 hours. The car's average speed in meter per second is equal to. Please pause this video and try to solve this problem. So the solution of this problem is speed is equal to total distance divided by the total time. So it's going to be 180 km divided by 2 hours is going to be 90 km per hour. In the previous lecture, I have mentioned a shortcut to convert from kilometer per hour to meter per second is going to basically be that you divide by 3.6, you are going to get an answer in meter per second. So 90 divided by 3.6 is going to be 25 meters per second. So this actually tells us the average speed of that car in that time slot of 2 hours. It's equal to 25 meter per second. So every 1 second we have covered 25 meters. Every 1 second we have covered 25 meters. Let's see an example 2. A cat runs 4 meter in 5 seconds and then 8 meter in 10 seconds in the same direction. The cat's average speed in meter per second is. Please pause this video and try to solve this problem. So let's see the solution of it. Again, the speed is total distance divided by the total time. So the total distance we have traveled is 4 and 8 meters. So it's going to be 4 plus 8. And total time we have traveled is 5 and 10. So it's going to be added together. So the average speed is going to be equal to 0.8 meter per second. Position time graph is a graphical representation of how the object's position changes over time. In the x-axis of this graph we have time, and in the y-axis we have position. Now you may ask yourself that why the position is on the y-axis and why the time is on the x-axis. It's because position is a function of time. In other words, position is a dependent variable, whereas time in this case is going to be an independent variable. So always the dependent variable lies on the y-axis and an independent variable lies on the x-axis. When the position is equal to 0, it means I'm at the origin, and if the position is positive, I have moved forward or I have moved towards the right. If I'm going to consider an x-axis, I have moved forward. If the position is negative, it means I have moved in the negative x direction. Let us consider this graph here, and we will see each of these locations one by one. Let us say I am 10 meters away from the origin and I have started my stopwatch. From 0 second to 2 second at B, the position didn't change. The position didn't change, which means what? That if the slope of position time graph is 0, the object is standing still. It is actually at rest. Now let us examine B to C. To travel from B to C, I have to move 10 meters backward to reach to x equals to 0. This B to C path indicates a negative slope. So whenever I have a negative slope in the position time graph, it's going to be moving backward. It's going to be moving backward. So if I'm going to examine now C to D, it does not have any slope. It means what? That the object is standing still. The object is standing still. From D to E, again the slope is negative, and I have covered from x equals to 0 to x equals to negative 15, which means I have moved backward. From E to F, again the slope is equal to 0, which means what? I'm at rest. I'm standing still. From F to G, the slope is now positive. The slope is positive. So in this case, I'm moving forward. So I have traveled from starting from x equals to negative 15 to x equals to 0, and eventually from G to H I have moved forward because the slope is positive. So by examining this position time graph, we can calculate the distance, and also we can calculate the displacement. The distance is going to be equal to the summation of all the distances mentioned in this graph, regardless of the direction. So I'm going to just add them algebraically. It's going to be 10 plus 15 plus 15 plus 15 equals to 55 meters. In the case of the displacement does not care about what path I have chosen to move from location A to location H. I just need the final position and I just need the initial position. So displacement is going to be equal to final position. How much is the final position we have here? We have x equals to 15 as final position and x equals to 10 as initial position. So it's going to be 15 minus 10 equal to 5 meters. As we have discussed about the slope of the position time graph, the slope of the position time graph is actually known as velocity. The velocity is actually the rate of change of displacement with respect to time. There are two types of velocities. One is average velocity and other is instantaneous velocity. Now let us consider this graph, and this graph is a position versus time graph and it is non-linear graph. Let us pick 2 points from this graph, let's say A and B. If I'm going to say that B is the final position and A is the initial position, I can get the displacement, which is going to be final position minus the initial position divided by the final time minus the initial time. I'm going to get a average velocity. If I'm going to reduce the denominator, which is basically delta t, to approach to 0, so it means what I'm taking a limit and delta t is approaching 0. In other words, this means that I'm taking a derivative of x with respect to time. In other words, if I'm going to move this B very close to A, this means what delta t is actually approaching 0, I'm going to get a tangent of this curve at location A, which is actually indicated as a green color in this graph. So for calculating the instantaneous velocity, I have to know the function of this graph if it is non-linear, if it is a non-linear graph, and I have to take its derivative with respect to time. The velocity is a vector quantity, so it's going to have direction. As I have mentioned, the position time graph slope can be positive, which means I'm moving forward. It can be negative slope, which means I'm moving backward, and if it is a constant, it means I'm at rest. So the slope is actually equal to the velocity. Let us see an example. The figure represents the position time graph of a particle between t equals to 0 and t equals to 5 seconds. What is the average velocity of the particle? So the initial position of this particle is at -10 and the final position is at 50. The final time is 5 and the initial time is 0. Please pause this video and try to solve this problem. The velocity is equal to rate of change of displacement with respect to time. So final position was 50 minus initial position is -10, so it's going to be 50 minus -10 will give you 60 divided by final time minus the initial time will give you 12 meter per second, and it's a positive value, which means the slope is positive and I'm moving forward. So I have moved from x equals to -10 to x equals to 50 by moving forward. So this is actually indicating the slope of this line, and you can see that it's not actual, it's an average velocity. If I want to calculate instantaneous velocity, I have to actually take a derivative of the function if I know the function of this graph. Let us see an example for a particle moving on a straight line. It changes its position from x1 equals to 100 meter at t1 equal to 2 second to x2 equals to 50 meter at t2 equals to 6 second. Now you can see that final position is less positive than initial position, which means what I have to move backward. What is the average velocity of the particle? Please pause this video and try to solve this problem. So again, the v is equal to delta x over delta t. So it's going to be 50, which is final position, minus 100 initial position, divided by 6 final time minus 2 initial time. I'm going to get it as minus 12.5 meter per second, and negative indicates that I have to move backward. And to understand meter per second, in 1 second I have traveled 12.5 meters backward to reach from x1 equal to 100 to x2 equal to 50. Let us see an example 5. The position of a body moving along a straight line varies with time t as x equals to 4t square minus 20t. So the function is given to us with respect to time, where x is in meters and t is in seconds. Find the average velocity from t equals to 0 to t equals to 3 seconds. Please pause this video and try to solve this problem. Since it is average velocity, the average velocity is delta x over delta t. I need to know x1, I need to know x2. So what I have to do is I have to substitute t equals to 0 and t equals to 3 seconds to get x1 and x2. x1 is equal to 0 and x2 is going to be equal to minus 24 meters. So if I'm going to substitute the x2, x1, t2 and t1 in the formula, I'm going to get minus 8 meter per second, and again negative indicates that I'm moving backward. And in the case of the graph, this means what? The slope of the graph is going to be negative. It's going to decline. Let us see example 6. The position of a particle moving along the x-axis is given by x equals to 6t square plus 10, where x is in meter and t is in second. What is the particle's instantaneous velocity in meter per second at t equals to 4 seconds? So I have to now find instantaneous velocity. Please pause this video and try to solve this problem. So in order to find the instantaneous velocity, we have to take a derivative of x with respect to time. So the derivative of this is going to be equal to, we have to use a power rule. So it's going to be t square, it's going to reduce to t to the power 1, and 2 is going to come down. So it's going to be 6 times 2, 6 was constant there, so 6 times 2 is 12. T to the power 2 minus 1 will give you t, and the derivative of a constant is going to be equal to 0. So you are going to get v equals to 12t. So if I'm going to substitute t equals to 4 seconds in this, I am going to get 48 meter per second, and it's a positive value, which means what? The slope is going to be positive and I'm moving forward. Let us see this example. The coordinate of a particle moving along the x-axis is shown in the figure. At what time in second is the particle momentarily at rest? Please pause this video and try to solve this problem. As we have mentioned, zero slope of a position versus time graph indicates that I'm at rest or the object is at rest. So in this case, the slope at the top here at t equals to 1 is 0, and the slope at t equals to 3 is equal to 0. So at t equals to 1 and at t equals to 3, the object is going to be at rest momentarily. After finding the velocity from the position versus time graph at various time intervals, we can plot those points to create a velocity versus time graph. Velocity versus time graph will have the velocity on the y-axis because it is a dependent variable and it's going to be a function of time, whereas time is on the x-axis and it's going to be an independent variable. When the graph is on the x-axis, the velocity is equal to 0, which in other words means that the object is at rest. So in this example, when time is equal to 0, when time is equal to 5, and when time is equal to 8 seconds, the object is at rest. All the graph that is above the x-axis will be having an object moving forward, and all the graph that is below the x-axis will be having an object moving backward. Let us discuss when the object is moving forward. So when the object is moving forward and the slope of the graph is positive, it means that the object is speeding up. When the slope is 0, it means the object is moving with the constant velocity. Again, it is speeding up. And when the slope of the graph is negative and the graph is above the x-axis, it means that the object is slowing down, but the object is still moving in the positive x direction. When the graph is below the x-axis, the object is moving backward, and when the slope is negative and the graph is below the x-axis, the object is speeding up, but it is moving in the negative x direction. And if the graph is having a positive slope and it's below the x-axis, it means that the object is slowing down, but still it is moving in the negative x direction. The slope of the graph, the slope of the velocity versus time graph is known as acceleration, and we are going to discuss acceleration in a while. And the area under the velocity versus time graph is going to give us displacement or distance. So let us see an example in which we can calculate the displacement or distance of this velocity versus time graph given to us. To find the displacement or distance, we have to divide this graph into multiple sub areas. So this is area 1, which is triangle, area 2 is a square, area 3 is a trapezoid, area 4 is a triangle, area 5 is a triangle again, and area 6 is again triangle. So when finding the area of all of these shapes, we are going to get an answer in meters. So area 1 is equal to 2 meters, area 2 is equal to 4 meters, area 3 is going to be 5 meters, area 4 is going to be 6 meters, area 5 is going to be minus 6 meter, area 6 is going to be minus 3 meters. And if I want to find the displacement, I just need to add all of these values, also considering the negative sign, will give me the total displacement. And when I want to find the distance, I have to make all the negative values to become positive values, and I will add all of these numbers to give me a total distance equal to 26 meters. As we discussed earlier, that the slope of the velocity versus time graph is known as acceleration. So let us discuss the acceleration in detail. In other words, the acceleration is the rate of change of velocity with respect to time. There are two types of acceleration which we are going to discuss here. One is average acceleration and the other is instantaneous acceleration. When we want to calculate the average acceleration, we can pick any 2 points from the velocity versus time graph, considering it to be final velocity minus initial velocity divided by final time minus the initial time is going to give us an average velocity. But if we want to calculate an instantaneous acceleration, an acceleration at any specific time, at any instant, we can calculate it by taking the derivative of the velocity versus time graph function. So it's going to be the derivative of velocity as a function of time, and we are going to take its derivative with respect to time. Let us see this non-linear velocity versus time graph and see how the variation is there with respect to the acceleration. So from time equal to 0 to time equal to 2 seconds, the slope of this graph is positive, which means what, the object is speeding up. In other words, the acceleration is positive. When the time is equal to 2 seconds, the slope is equal to 0, which means the acceleration is equal to 0. So we can calculate the slope at these points, and the value of the slope will give us the acceleration, and we can plot an acceleration versus time graph. So when time was equal to 0, the acceleration was equal to 20. When time is equal to 1, the acceleration was equal to 10, positive, because it was speeding up and the slope was positive. When the time is equal to 2 seconds, the acceleration is equal to 0. But we need to look carefully the interval of time equal to 2 to time equal to 4. Since it is above the x-axis and the slope turns out to be negative, the object is slowing down. So if the slope is negative, in other words, the acceleration is negative. So it means what? The acceleration is opposite to the movement. Since the velocity versus time graph was above the x-axis, the object is still moving forward. But the acceleration is trying to slow it down, so it is acting in the opposite direction. So this phenomena is known as deceleration. So a phase from time equal to 2, just after 2, to time equal to 4, just before 4, this process is known as deceleration. The object is slowing down due to deceleration. When the velocity versus time graph is below the x-axis and its slope is negative, the object is speeding up, but it is moving in the negative x direction. So we can see from time equal to 2 to time equal to 5, all the values of the acceleration are negative and increasing, and all these values indicate the acceleration is acting in the negative x direction. But the time interval between t equal to 2 to t equal to 4 seconds, the object is still moving forward, but it is slowing down. But the acceleration is negative. Because it is actually a reason which is causing an object to slow down. In summary, when we have a position function with respect to time, we can take its derivative and we can get velocity. If we take a derivative again of a velocity function, we can get acceleration. If we want to move backward, we have to take antiderivative, which is basically a integration. So if I have an acceleration function, if I integrate that function, I will get velocity, and if I again integrate velocity function with respect to time, I will get the position function again. As all the graphs are related to each other, let us have a summary of all different types of scenarios. So for example, if the position function is a cubic function, for example x is equal to some constant a t cubed, if I take its derivative, the derivative is going to give me a velocity graph, and it's going to start at 0, but it is going to increase quadratically because the t is having a power of 2. If I take its derivative again, it's going to give me a linear acceleration graph because the power of t is equal to 1, and it's going to start at 0, but it is going to increase linearly for this example. If I have a square function of position, for example, x is equal to some constant b times t square. If I take its derivative, will give me a velocity graph. So it's going to be starting from 0 and it's going to increase linearly because the time will have a power equal to 1. If I take its derivative again, it's going to give me an acceleration graph. Now in this case, the acceleration graph is going to be constant non-zero value. So it's not going to have any slope, it's going to be a constant graph. If the position function is linear, which means the power of t is equal to 1, x is equal to some constant c times t. If I take the derivative of this function, will give me the velocity and it's going to be a constant non-zero value. It will not have any slope because the time has a power equal to 0. So v is going to be equal to some constant c. So if I'm going to take a derivative of this constant velocity, the acceleration is going to be equal to 0. So based on this information, we can plot our graph. If any one of the graph is given, we can plot the other graphs by this relationship. Let us see this example. If we are given a position versus time graph something like this, we can plot the velocity versus time graph, and after that we can plot the acceleration versus time graph. So for example, when time is equal to 0, the slope of this graph is equal to 0, which means what? The velocity is equal to 0. At this time, the slope of this graph is negative, which means the velocity will have a negative value. At this time, the slope became 0, which in other words means that the velocity is equal to 0. At this time, the slope is still 0. It means the velocity is still equal to 0. And here the slope became positive, which means the velocity will have a positive value. So if this is a square function from here to here and then constant and then a square function, the velocity versus time graph from here to here, it's going to be a linear line and then constant and then again a linear line, considering this part and this part to be a square function. Now from the velocity versus time graph, we can plot the acceleration versus time graph. So considering this part, we have a constant negative slope from here to here. So it means that the acceleration will have a negative value. From here all the way here, we have a positive slope, which means what? The graph of acceleration is going to move or is going to jump from negative to positive, and it's going to be still constant because this is a linear line. So we are going to have a constant acceleration at this region, positive. From this time to this time, the velocity is equal to 0, which in other words means that the acceleration is equal to 0 because the slope is also equal to 0 and the velocity is also equal to 0. So it's going to be having a equal to 0 at this location. When the slope of the velocity versus time graph is positive and it's linear, it will have a constant slope which is going to be a positive value, and it's going to be basically acceleration positive value. So if the function was t square from here to here and then it was not having any function of time, it's a constant value of position, so it can be any value, for example negative 10 meters for example. It's not going to be a function of time, it's going to be a constant, and again it's going to be a function of time as t square. So if I take a derivative from here to here of this function, it's going to give me t to the power 1. So it means it's a linear function. And again, if this is a square function, position time graph, it's going to be a linear velocity time versus time graph function, which in other words means t will have a power equal to 1. At this location, it was a constant position, which means the object is at rest, the velocity is going to be equal to 0. So it's not going to have any slope, and it's not going to have any velocity. Which means what? If you are taking a derivative of a constant, it's going to give you a 0 value of velocity in this portion. If you take a derivative of t square again, you are going to get t to the power 1, and it means it's a linear function. So if you take the velocity versus time graph derivative again, this t to the power 1 function will become a constant graph. Again, t to the power 1 will become constant graph. If you take a derivative of 0, it's again going to give you a 0. And if you have a positive some slope, and it's basically t to the power 1, the derivative of that is going to be a constant non-zero value. Let us see example 9. The position of a particle moving along the x-axis is given by x is equal to t cube minus 4t square plus 2t minus 10, where x is in meters and t is in seconds. What is the instantaneous acceleration a in meter per second square of the object at the time equal to 2 seconds? Please pause this video and try to solve this problem. To find the instantaneous acceleration, first of all we have to take a derivative to get the velocity, instantaneous velocity, and by taking the derivative of the instantaneous velocity with respect to time, I'm going to get the acceleration function with respect to time. So you can see that it was a cubic function of the position versus time graph. I took its derivative, it became t square, and then if I took a derivative again, it's going to be a linear acceleration function because the power of time has become 1. So if I'm going to substitute t equals to 2 seconds in this, I'm going to get the acceleration equal to 4 meter per second square, and it's a positive value, which means I'm speeding up in this location, and the acceleration is going to be in the positive x-axis. Let us see this example. The acceleration time graph for an object is shown in the figure. During which time interval is the object moving with constant velocity? Think about it and try to solve this problem. We have an acceleration versus time graph given to us, and we want to find at which time interval the object is moving with constant velocity. So if you take a derivative of any constant velocity value, it's going to give you acceleration equal to 0. So and in the time interval of t equal to 2 to t equal to 3 second, the acceleration is equal to 0. So this time interval will have a constant velocity, whereas all of these constant acceleration value is a non-zero value, which means what, there is going to be a velocity as a function of time, and it's going to be t equal t to the power 1. So if you take the derivative of that, it's going to give you a constant acceleration, non-zero value. But if you have a constant velocity, if you take the derivative of the constant velocity, it's going to give you zero acceleration, as we discussed this thing in that table as well. Thank you so much, and I will see you in the next lecture.